Section 7.3, Names and Formulas for Ionic Compounds. The objective of this lesson is to relate a formula unit of an ionic compound to its composition, write formulas for ionic compounds and oxyanions, applying name conventions to ionic compounds and oxyanions. Some vocabulary to review is nonmetal. Some new vocabulary will be formula unit, monoatomic ion, oxidation number, polyatomic ion, and oxyanion. Because chemists around the world need to be able to communicate with one another, they have developed a set of rules for naming compounds. Using this standardized naming system, you can write a chemical formula for a compound's name and name a compound given its chemical formula. Recall that an ionic compound is made up of ions arranged in a repeating pattern. The chemical formula for an ionic compound, called a formula unit, represents the simplest ratio of the ions involved. For example, the formula unit of magnesium chloride is MgCl2 because the magnesium and the chloride ions exist in a 1:2 ratio. The overall charge of a formula unit is 0 because the formula unit representing the entire crystal, which is electrically neutral. The formula unit for magnesium chloride contains 1 magnesium ion and 2 chloride ions for a total charge of 0. Binary ionic compounds are composed of positively charged monoatomic ions of a metal and negatively charged monoatomic ions of a nonmetal. A monoatomic ion is a one-atom ion, such as magnesium or bromide. Table 7.7 below indicates the charge of common monoatomic ions according to their location on the periodic table. What is the formula for the beryllium ion, the iodide ion, and the nitride ion? And again, if we take a look at this chart down here, right, remember that we could also go ahead and look at the periodic table to go ahead and determine what are the charges, right? Everything in group 1 has that positive 1 charge. Everything in group 2 has a positive 2 charge, right? Jump to transition metals. They have their own sets of rules. Go to group 13. Those are positive 3. Group 14 could either be positive 4 or minus 4. Group 15 is minus 3. Group 16 is minus 2. Group 17 is minus 1. And again, our group 18 elements are our noble gases, and they tend to not like to do any sort of bonding whatsoever. Transition metals, which are in groups 3 through 12, and metals in groups 13 and 14 are not included because of the variance in ionic charges of atoms in the group. Most transition metals and metals in group 13 and 14 can form several different positive ions. And again, these are your post-transition metals that can do that. So here are some in table 7.8, some monoatomic metal ions. Right? You can have the same element, but they'll have different charges. Another way we can go ahead and talk about charges is using the term oxidation state. So you're going to hear me start using the word oxidation state a little more than I'm going to be saying charges. Right? In this case, right, group 4 elements in your transition metals, titanium can exist as a +2 or a +3. Vanadium can exist +2, +3. It goes on, and it goes on. It just kind of follows their own little rules, right? Even if you look at lead over here, lead and tin, your post-transition metals can have 2 different charges. Good hard and fast rules when using that periodic table. Everything that is in your metalloid staircase and above will generally follow that periodic table trend. The charge of a monoatomic ion is known as its oxidation number or its oxidation state. Again, that's just a chemistry way of saying charge. As shown in 7.8, most transition metals and group 13 and 14 metals have more than one possible oxidation state. Note that the oxidation number given in 7.8 are the most common ones. And again, this is not the only possible ones. The oxidation number for an element in an ionic compound equals the number of electrons transferred from the atom to form the ion. For example, a sodium ion transfers 1 electron to a chlorine atom to form sodium chloride. This results in a positive sodium ion and a negative chloride ion. Thus, the oxidation number of sodium in the compound is +1, because 1 electron was transferred to from the sodium atom. Because an electron is transferred to the chlorine atom, its oxidation number is -1. In the chemical formula for any ionic compound, the symbol of the cation is always written first, followed by the symbol of the anion. Right? It's always cation, anion. Subscripts, which are small numbers to the lower right of a symbol, represents the number of ions of each element in an ionic compound. If no subscript is written, it is assumed to be 1. Right? We don't write 1. We would just generally leave it blank because, again, if you have 1 sodium ion and it's labeled as Na, right, it's already stated because Na is there. Right? So no subscript, right, usually means 1, and it would be improper to even just put 1 there as well. You can use oxidation numbers to write formulas for ionic compounds. Recall that ionic compounds have no charge. If you add the oxidation number of each ion multiplied by the number of these ions in a formula unit, the total must be 0. Suppose you need to determine the formula for 1 formula unit of the compound that contains sodium and fluoride ions. Start by writing the symbol and charge for each ion. Right? In this case, sodium is +1 and fluoride is -1. The ratio of ions in a formula unit of the compound must show the number of electrons lost by the metal equals the number of electrons gained by the nonmetal. This occurs when 1 sodium ion transfers 1 electron to the fluoride ion, and the formula unit is NaF, right? Sodium fluoride. Determine the formula for the ionic compound formed from potassium and oxygen. And if we were to go ahead and go back to our periodic table, right, we can go ahead and look and find that potassium is a group 1 element and oxygen is a group 16 element. Because potassium is group 1, we know it's going to have a positive 1 charge, and oxygen, group 16 element, it's going to have a -2 charge. So when we put it up like this, right, we can go ahead and put them together, right? I like to just go ahead and look at the superscripts, and then I take those superscripts and I swap them to be the subscripts of the adjacent element, and then we get K2O, right? You can even go ahead and evaluate your answer in such a way that it's going to take 2 potassium ions to transfer to 1 oxygen so that it becomes chemically neutral. Again, we wanted to go ahead and determine the formula for the compound joined from aluminum ions and sulfide ions. Right? Let's just go back and look at the periodic table. Right? Aluminum, right, has a +3 charge, right, group 13 element, and group 16 element sulfur has a -2 charge. So we're dealing with aluminum +3, sulfur -2. Again, when we take those superscripts and we swap them to the adjacent elements, subscripts, we should get Al2S3, right? Or better known as aluminum sulfide. Many ionic compounds contain polyatomic ions, which are ions made up of more than 1 atom. Tables 7.9 and 7.10 list the formulas and charges of common polyatomic ions. You could also refer to your appendix. They have more of them as well. Polyatomic ion acts as an individual ion in a compound, and that is charge applies to the entire group of atoms. All right, let me say that again. A polyatomic ion acts as one individual ion that is in a compound, and that charge applies to that whole group of atoms, and that whole thing is charged. right? Thus, the formula for the polyatomic compound follows the same rules used for a binary compound. Because a polyatomic ion exists as a unit, never change the subscripts of the atoms within that polyatomic ion. If more than one polyatomic ion is needed, use parentheses around the ion and write the appropriate subscript outside of the parentheses. For example, consider the compound formed by ammonium ion. Ammonium should be NH4. That looks like a typo right there. This should be NH4 plus 1. And again, you can see that ammonium is right down here, right? And the oxide ion, which is oxygen minus 2. To balance the charges, the compound must have 2 ammonium ions for each oxide ion. To add a subscript to the ammonium enclosed in parentheses, right, then add the subscript. So we take that 2 from the oxygen and put it outside the parentheses of the ammonium, and because ammonium has a plus 1 charge, right, that 1 on the oxygen is already implied. So when looking at your common polyatomics, we have quite a few of them. Right, you have ammonium nitrite, nitrate, right? Big difference here. Nitrite ends in ITE, nitrate ends in ATE. You have hydroxide, cyanide, permanganate, right? Hydrogen carbonate, hypochlorite, then you have chlorite, but you also have chlorate and perchlorate. Right? If you were to go ahead and look at these 4 in particular, perchlorate, right? 8 usually means it has a greater number of oxygens, right? Just as we did with nitrate. Nitrate has a greater number of oxygens than nitrite. But because we already have a chlorate, in this case, perchlorate has 4 oxygens associated with it. Perchlorate, chlorate, chlorite has less amount of oxygens, right? Only 2 in this case. But the lowest amount of oxygens that you could have is hypochlorite, right? Hypo is a prefix, right? Like hypothermia means low. So that's kind of a way that you could remember it. Now, I'm not going to go through all these polyatomics. I'm just going to go ahead and let you guys get familiar with them. Right? That's going to be a you thing. It's just going to take some time to go ahead and identify them and how they work. Practice, practice, practice. All right. A compound formed by calcium ions and a phosphate ions is often used in fertilizers. Let's go ahead and write the chemical formula for that. Right, again, let's go ahead and look at our periodic table. We'll see that calcium is a group 2 element, which means it's going to have a plus 2 charge. We also know that phosphate, right, is a polyatomic ion that has the formula of PO4 minus 3. Right? We're going to go ahead and swap those charges so that they become superscripts. But because we need 2 phosphates to balance out the calciums, the 3 calciums from the phosphate, we need to go ahead and put parentheses around your phosphate and then put that 2 outside the parentheses of your phosphate to go ahead and tell us that we have 2 phosphates but not one phosphorus and then 42 oxygens. And this is kind of why we use the parentheses system. We don't want 42 oxygens with this compound because it would not be calcium phosphate. Scientists use a systematic approach when naming ionic compounds. Because ionic compounds have both cations and anions, the naming system accounts for both of these ions. An oxyanion is a polyatomic ion composed of an element, usually a nonmetal, bonded to 1 or more oxygen atoms. More than one oxyanion exists for some nonmetals, such as nitrogen and sulfur. These ions are easily named using the rules below. Right? So we're going to go ahead and identify the ion with the greatest number of oxygen atoms. This ion is named using the root of the nonmetal as the suffix -ate. Then we're going to go ahead and identify the ion with fewer oxygen atoms, and this ion is named using the root of the nonmetal -ite. So for example, right, here we have NO3 and NO2. Because NO3 has more than NO2, more oxygens, NO3 minus 1 gets the name nitrate, whereas NO2 minus 1 gets the name nitrite. Right? Same thing that goes with sulfate and sulfite. Sulfate is SO4 minus 2, whereas sulfite is SO3 minus 2. Right, as shown in the table next to us, chlorine forms 4 oxyanions that are named according to the number of oxygen atoms present. Names for similar oxyanions formed by other halogens follows the rules used for chlorine. For example, bromine forms the bromate ion, and iodine forms the periodate ion, and the iodate ion. Chemical nomenclature is a systematic way of naming compounds. Now that you are familiar with the chemical formulas, you can use the following 5 rules to name ionic compounds. Right? Number 1 is name the cation followed by the anion. But remember that the cation is always written first in the formula. For monoatomic cations, use the element name. For monoatomic anions, use the root of the element name plus the suffix IDE, right? So in this case, if we had cesium and bromide, we would go ahead and combine the two of them, right, to call them cesium bromide. To distinguish between multiple oxidation states of the element, the name of the chemical formula must indicate the oxidation number of the cation. And this usually applies to your D block elements when we need to go ahead and use the Roman numeral. Right? Your representative elements usually don't, this doesn't apply to your representative elements, but definitely your transition metals and most likely your post-transition metals as well. The oxidation number is written as a Roman numeral in parentheses after the name of the cation. And just note, this rule applies to the transition metals and the metals on the right side of the periodic table, right? Your transition and your post-transition metals, which often have more than one oxidation state. If it doesn't apply to group 1 and group 2 elements, as they only have one oxidation number, right? Such is the case of iron. Iron can exist as a +2 or a +3. When we go ahead and combine them, right, Fe, iron +2 and oxygen, we would get FeO, right? Notice that these had like charges, and we were able to go ahead and reduce them in the process. So that's why we get FeO. But when we're going to talk about this compound, we call it iron 2 oxide, right? Because iron has a +2 charge. And again, we can also note that iron has a +2 charge, is if you know that oxygen will always have a -2 charge, what happened to that 2 that's supposed to show up on iron? Well, it must have been reduced to 1 because there was like integers to go ahead and reduce that. In this case, iron +3 and oxygen ions form Fe2O3, right? And again, we knew that oxygen had a -2 charge, and look at that, it shows up on the iron here when iron has a +3 charge. And if we wanted to go ahead and name this, right, we have to go ahead and call it iron 3 oxide. And again, these Roman numerals tell us the oxidation state of the metals. When the compound contains a polyatomic ion, simply name the cation followed by the name of the polyatomic ion, right? For example, if you had NaOH, right, which is just known as sodium hydroxide. And if we had NH4(2)S, right, this is known as ammonium sulfide. And again, if we were to go ahead and have a compound with a transition element, a transition metal or a post-transition metal, we would also need to go ahead and state the oxidation state as well, right? Case in point, if we were to look at this example right here, copper with a nitrate, right? In this case, we know that nitrate has a -1 charge, right? And this 2 came from the copper, right? So we know that the oxidation state of copper is +2. So we would call this copper 2 nitrate. And here's a little flow chart to go ahead and help you name ionic compounds. The problem-solving strategy above reviews the steps used in naming ionic compounds. If the formula is given, naming ionic compounds is important in communicating the cation and anion present in a crystalline solid or aqueous solution. How might you change the diagram to help you write the formulas for ionic compounds if you didn't know their names? The ion containing substance you have investigated so far have been ionic compounds. In the next section, you will learn how ions relate to the structure and properties of metals. Section summary. A formula unit gives the ratio of cations to anions in the ionic compound. A monoatomic ion is formed from one atom. The charge of a monoatomic ion is its oxidation number. Roman numerals indicate the oxidation number of cations having multiple possible oxidation states. Polyatomic ions consist of more than one atom and act as a single unit. And to indicate more than one polyatomic ion in a chemical formula, place parentheses around the polyatomic ion and then use the subscript outside the parenthesis.